Hey, what's up, guys? John here. So today, let's take a look at another LeetCode problem here. 1269, number of ways to stay in the same place after some steps. Okay, so you're given like two parameters. First one is the steps you can take, and the second one is the length of this array. All right, and at each step, you can do three things. You either move to the left, you move to the right, or you stay, or you don't move. And you start from from the zero index, 0, 1, and 2. Uh, or at index 0, yes. So uh, position, right? P array here. There's an array here, and there's index 1, 2, and 3, right? So you start with 0, and and in the end, after uh, steps, after this many steps here, you need to come back to the 0, right? Okay, then it asks you to find out all the possible ways of doing so, doing the same thing, right? Doing the all the possible ways of moving in the end, moving back to the 0 index here, and you cannot move outside of this array here, right? So okay, so what's our solution here, right? So we can use like dynamic programming, a DP solutions, right? Basically, we simply do a 2D array, right? Basically, we're gonna have like DP and DP ij. Okay, right? That's what we usually do the DP here, right? So what does the DP ij means, right? It means the at uh, at steps I and an index and index j, how many ways we can get to here. Okay, right? So since we have two variables here, we simply just use those two variables to define the dpij, which we are like at step I and position and index j, how many ways we can get here, right? And in the end, we just return what? We return we return the steps here, right? The steps and 0, right? Which means at steps at this after this steps and then at the position 0, which is the result we need, right? How many ways we can get here, right? Because in the end we need to come back here, right? And then okay, so then the question comes down to how can we uh, get this dpij, right? So let's take a look. How many ways we can get to this ij, right? basically you can do three movements, right? So you either do left, right, or don't move, right? So let's okay, dpij, right? So the first one is don't move. So if you don't move, what does it mean, right? It means that it's a dp uh, I minus 1 and j, right? That's the steps, right? Basically, this means like if you don't move, right, you're still at the position j here, right? And if you don't move means that the same result, right? The same result as a previously step, right? That's the don't stay. And then you can come to here moving from left, right? So that's the dp uh, I minus 1 plus then j minus 1, right? So that's the so this is the like so you're moving from left to this position. And another third one is you move from the right, right? You can also moving from the right position to here, right? Which is the on the previously basically this means on the previous step you are at the right position. So and then now you can come to here, right? So that's yeah that's the DP function here basically, right? And then yeah I think we can just start. Yeah, it's pretty much everything about this DP problem. And yeah, okay, let's start coding. I will talk a little bit more while we're coding here. So since we have that function DP functions here, so all we need we need to get this what is that? And I'm gonna do a m and n. Okay, so m equals to steps, right? That's how many steps, and n equals to the array. Okay, but here, all right. Okay, I'll finish the DP algorithm here, and then we'll talk about some improvements here. So basically here, and we're gonna create a 2D array here, and the initial stat 0. So and n for in range m plus 1. Okay. So the reason I'm doing a m plus 1 is that we'll be since we're going to get the previously step, right? And I need to have like step 0 as a starting point. So what that it means that the 0, 0 is equal to 1, right? And let's do a for I in range m and for j in range n. Sorry. So here it's starting from I to m. Basically, this thing means like at step 1 because we already know at step 0 and at index 0 the initial step will be 1, right? So now we move to step 1 here. And for step 1 basically we check all the uh, each of the range, right? So and like I said dp I j, right, equals to what? Equals to the so mm, so first is the state, right? Basically we come from the previous state and move to here. And second one is the moving from left, right? J minus 1. And you can also move from the right, uh, J plus 1, right? But since here we have a, like conditions here, you cannot move outside of the array here. So that's why we need to do a check here, right? Basically, if the j, right, if the j is is equal to 0, right? What does it mean? It means that we cannot move from the left, right? If it's 0, it means is this gonna be out of the the boundary. So I'm gonna do a simple if else here, right? So I would simply do this. If the I is equals 0, so we only have two ways of doing it. Basically, stay and moving from right? Else if same thing for the other side to n minus 1, right? Same thing here, but instead I'm gonna remove the last one here. I'm gonna remove this one, right? And then else, right? And then else we do this, right? So in the end, we just return the dp m and 0. All right, so that's the at m steps and at zeros, how many ways we can get here, right? So this thing should just work, I think. Nah, let's see. Did I do anything wrong here? Oh, sorry. So since we're gonna also define a mod here, plus 7 and let's see. Did I do anything wrong here? Else dp m0. Okay, let's see. Oh, I think I know why. So since we're doing this like steps to m plus 1, we have to uh, loop through from 1 to m plus 1, not m. Yeah, so this thing work, but if you run it, if you run the see this length here, right? The length is like the length is like 10 to the 6, 10 to the power of 6, and which means the length will be like in this. So 10 to the power of 6 times 500, I think it's going to be too much. So how can we minimize, right? How can we improve this performance, right? So if you notice that here, right? So we have the steps is like it's bounded to 500 here, right? So and we have a index here, right? From 0 to like 10 to the 6 of to the 6, right? And then we have a steps up to 500, right? So and our final goal is to come back to the 0 here, right? Then you can see we don't need to loop through everything. We don't have to loop through all the n arrays here, right? Because the n array it's too long. All we need, let's say it's up to 500, right? And then the maximum we can go is 250, right? Because we need another 250 steps to come back to the 0, right? If we are like exceeded this 250s, then it means that we will never be able to come back to the starting point, right? So with that in mind, we can simply just do a quick check here, right? So we don't use this array here because we notice that this array size is way too big than we really need. We can use the minimum, right, of the steps divided by 2 plus 1, right? We just do a plus 1 just to make sure we're not removing the boundaries here. And this thing, right? So whichever is smaller, right? If this like is way bigger than the steps, we don't need to use everything. We can still use the like this much, then it's enough, right? So let's try it. Yeah, so it passed. All right. Yeah, pretty straightforward dynamic programming problem. So, two things, right? So one thing is that you have to come up with this like dynamic function here, right? Basically, from the current for this like with the I step and the j index, how can we get to the current state from the previous state, right? It's basically three ways: stay, move from the left, and then move from the right. And then we simply do some like check here, right? And remember here, since we need to get from the previous step, right? That's why we need to set the previous step, the starting as one. It means that, for example, at step one and at index zero, right? If we didn't set this thing to one, basically we'll never get any result because as you notice here, we always do a summarize from the previous step, and if we don't have a one here, the DP 10 will be also one, right? Which means at step one, at index zero, we have nothing. We have zero ways of getting here, which is wrong. That's why we need to have a starting point here. And then the second one is the how can we improve our searching range, right? Basically, since we are need to come back to the starting point, we can just use the minimum of these two, also steps divided by two, right? Plus one. Uh, cool. I think that's it. That's pretty much it. It is what I want to talk about for this problem. Yeah. Okay. Thank you so much for watching the video, guys, and hope you guys like it. And see you guys soon. Bye bye.